Hi everyone. So in this video, we will solve 20 questions on recursive descent parsers with Backtrack. So this particular parser is very, less understood to most of the experience. So that's why we will solve many questions, which is around 20 questions, to make sure that you understand this parser very well. Okay, how does it work, why it work, and on different type of grammars, how it will look like. So all of the questions has been taken from standard university or standard books. So let's just get started and let's just start with the very first question here. So let's see this question number 1. What they are saying is that consider the given grammar below. How many times we need to backtrack to parse this particular string? Which means that this particular parser is a backtracking parser, right? As the name says that it is a recursive descent parser with backtrack. So it means that if we need to parse some string, then it may need to backtrack. And that's what they're asking, that how many times we need to backtrack if we want to parse this particular string for this particular grammar, right? So what does this backtrack mean? It is given to us in this particular question, which we are saying that if a production X gives Y is a failure, that means it returns false, then we count it as one backtrack. So you may not remember what is this recursive descent parser. So let me just quickly revise you that what was that, right? So see, let's suppose we have this particular grammar. Now we will write different functions for each of the non-terminal. So which means if these are the two non-terminals, then we will be writing two functions, one for E, one for T. And if E is the start symbol, then we will say that okay, A equal to E. I mean, we will be basically saying that okay, whatever E return may be true or false, and then we will be at the last we will be checking whether the last symbol is ending with some special character which is dollar, right? And then if that is the case, which means E is returning true, and the last is also some special character which is dollar, then we will say parsing is successful. Okay, so that's how we write the code. Now there will be two functions, one for E, one for T. Now let me just tell you that how we write the function. So for E, we will be writing T. We will first trying this production T, and then we will be trying T plus E, right? So we will be trying this T, and then we will be trying T plus E. So these are the two productions that we will try. Now for this E, so I'm writing E1 and E2. For these two productions, I'm saying this is E1, this is E2. Here I'm saying this is T1, T2, and this is T3. Okay, so I'm saying T1, T2, T3, and E1, E2 for these productions. Now what is the code for E1? It will be just T. So for E1, I will just say whatever T is returning, it will just T. And for the E2, which is this production, it is saying that A equal to T, which means T and then plus and then E, right? And then I will match with plus, then I will say that I will be calling E, and then I will be returning A and B and C. Okay. And similarly, we can write code for T. So if T is this, then we can write code for T also. How? Let's just see. See, T is this. So T1, T2, T3. These are the three productions, right? Now to write the code for T, we will say that for T1, it is just matching with int. For T2, it is matching with int, then star, then it will be calling T, and it will be checking whether all of them is true or not. If all of them is true, it will return true, right? And similarly for T3, it will be matching with this, then calling E, and then matching with closing parenthesis, and then it will be checking whether all of them is true or not. Okay. So based on that, it will be basically writing the code for this T3. Okay, hope you understood that how to write the code for T1, T2, T3. By the way, one more thing is that if you match, let's suppose the input string, if you are calling this, if you are matching, okay, for example, if you are matching for, let's suppose T2, if you are calling this T2, and if you are matching with int star, and then you will call T. But let's suppose initially it is not int, okay, initially it is star itself. Then since star is not matching with int, then A will return false, right? A will return false. If it is not int, I mean, if you are calling T2 and the start symbol, the current symbol is not int, then it will return false. Okay, let's suppose the current symbol is star and you are calling T2, then it will return false. Then this T2 won't proceed further, which means that for the sake of saying, I'm saying that you will call these three. Otherwise, like in actual implementation, let me just show you that, see. Yeah, so in actual implementation, you will be matching with int. If this is false, you won't be calling others. Okay, you won't be calling others. I'm just trying to make it a little simpler. That's why I'm writing it in 3 lines. Otherwise, it should be something like this, right? That if it is matching with int, then you will not be calling others. Okay, you will not be calling match star and this. I'm assuming this is C programming code. So which means that you can say that if this is false, then after this end, whatever is written, it won't be executed. Okay. So anyway, let's just start with the question number 1, what it is saying. So this was the question number 1, right? Now they are saying that how many times we need to backtrack to pass this particular string for this grammar, right? So let me go to the next page and let me write the string and the grammar both. So this is the string that we want to parse, and let's see what is the grammar. This is the grammar using which we want to parse this string, and the parser, by default the parser in all the questions are recursive descent parser. Okay, recursive descent parser with backtracking. Now let's just see. Okay, so for this particular question, what you need to do, you just need to check that how many backtrack you need to make. So first you will be having E, then E will be calling T, right? Then T will be calling the very first production int. Now tell me, is this int matching with the current symbol, this opening parenthesis? Since it is not matching, that is why you will do backtrack. So what is a backtrack? Backtrack basically means that if there is a fail, okay, if there's some capital symbol is saying that okay, there is a failure, okay, in the some production, okay, then you will use another production. So you will backtrack at T. Why? Because this T production got failed, right? Since this T production got failed, that is why you will backtrack at T itself. It is not the case that you will not backtrack at E, which means you will not try this. Okay, you will not try this. It's not like that you will try the E second production of E. No, you will try the second production of T itself because there was a failure at T. Okay, so that is why there is a failure at this point. So that is why you will try the second production at T itself. So which means you will say, okay, let me try int start T. Intuitively also you know that it will also fail because this int and this opening parenthesis again not matching. So you will again backtrack. Now tell me, where is the failure? The failure is again at T, right? It's not at E. It's not at E. It's again at T. So that is why you will say that okay, this is E, and then let me try the next production for the T, which is this one, right? Now see here, this and this is matching. That's good. So that's why you can proceed further. Now for this E, what is the very first production? E gives T, right? So you will try E gives T. You will try E gives T, and then this T gives int, right? So you will try the next production, which is T gives int. Okay. So let me write it. T gives int. And then you will say that okay, this int, this opening parenthesis is matching, this int is also matching, and then this closing parenthesis is also matching. That's really great. So that's why what will happen, since all of them is matching, so this T will say that okay, I'm success. Like now this time I'm success. So it will return true. It will say I'm success. So E will return true. So how many times you are backtracking? You're just backtracking 2 times, one time here, right? So what is the answer? Answer of this particular question is 2, right? So answer is 2. Right? You are backtracking here and you are backtracking here. Just 2 times you are backtracking. I hope you understood. Easy question, just to get started. Okay. Now let's just see the second question, which I have taken from this university. So what they are saying, what does the following code parse? See, they are saying match A and match X and match Y and match Q. So A, X, Y, Q. Now you can easily understand that answer is A. Why? Because you are matching with A. So if A, X, Y, Q is there, then it will return true. It means they are asking for A, right? A, X, Y, Q. Now let's see this question number 3, which is little variation of question number 2. Now they are saying match A or match X or match Y or match Q. Now can you tell me what is the answer? This is A, X, Y, Q, which means if all of them match, then only true. It is saying either this or this or this or this, and in the same order. Which means first it will try A. So A, then X, then Y, and then Q. So first it will try A, then X, then Y, then Q. Okay. So that is why D is the correct answer here. D is the correct answer here. So for D, you will write code something like this. Let's suppose if no, one of the option is this X, Y, A, Q. Let's suppose E is this option. Is this also true? Tell me. If this is MSQ and E is this option, is this also true? The answer is no, because E is saying first try X. Although in this question it might not, I mean in the real answer it might not even matter. But anyway, sometimes it will matter. We will see the order of production might also matter. But anyway, for this particular question, you will say that D is the only answer. E is not the answer. Why? Because E is saying first try X, then Y, then A, then Q. And here you are trying A, X, Y, Q. So that is why E is not the answer. Okay, and D is the answer because A, then X, then Y, and Q. See, first you will try A. If this is true, you will not even look further, right? Because of the short circuiting that we see in the C programming. Okay, if even if you don't know about the short circuiting or all, so just see here that if something is true, then true or anything. Okay, true or anything, whatever is written there. Okay, whatever is written there, true or anything is actually true. So that's why you don't need to look at what is this, right? True or anything. This is, if this is true, then or anything doesn't even matter. So that's why it will not look at the further things. So that's even called short circuiting in C programming, but let's not even worry about it. Okay, so that's why D is the correct answer here. Now let's see this particular question, okay, which is a little more variation of the previous two questions. So here what we are saying, match Q, match P, or match A and S. So this is interesting, isn't it? Now can you solve this? They are saying that QP. So you need to match Q and P first, or A, and then you will be calling S. So what is the answer? I think A is the correct answer, right? QP, A, and S. Okay. In this option, I think this is by mistake I have put 2 vertical bar, but that's fine. Okay. So this is AS, QP, no. This is QP, first you will be matching Q and P. And once you match this, if this is false, then or A and S, right? A and S. So I think A is the correct answer here. Okay. Now let's see this question. Can the below grammar be parsed by the recursive descent parser? What do you think? See, this grammar is left recursive, right? Since this grammar is left recursive, so you will say no because the grammar is left recursive, right? Because this grammar is left recursive, that's why you can't parse using recursive descent parser. Okay. Now let's just see this particular question. What they're saying. Consider the grammar given below. How many times you need to backtrack to pass this? Okay, that's interesting. And even like it might be little lengthy also, but let's just solve this, right? Let me go to the next page and let's just try solving this. What is the grammar that is given to us? Let me copy this grammar also. Okay. So first they are saying that you will try this S, capital S gives, capital S gives A, right? Then this capital A will try small a, capital B. And since this small a is matching, so that's really good. And then you will be trying this capital B. Capital B will say the very first production is triple B, right? Very first production here is triple B. Even there is just one production, that's fine. So now you will say that, okay, this and this is matching. And then this B is not matching with this D. Since this B and D are not matching, that's why this B is a failure, right? This B is a failure. So since this B is a failure, that is why you will backtrack here. Okay. See, tell me, is this B a failure? This A is a failure or S is a failure? What is a failure? Failure is this B, which means you will now try the different production of B. Okay. So tell me what is the different production of B? So you will backtrack and then you will try the next production of B. So what is the next production? Here, as you can see, there is no next production, which means there was only one production of B, which you have tried, which got failed, right? See, here you are saying, let's just backtrack. Okay, which is really good. We need to backtrack. And now you are saying that this B is having only one production, which means all of the production you have tried, all of them was failure. So that's why you will backtrack at A now, because you will say that this A will return false, which means that this A is a failure. Why? If B is returning false, then this A will return false. Then at this A, you will backtrack again. Right? Backtrack means that you will try the different production of A. Okay. So do you have any different production of A? This you have tried. Now you will be trying this AABA. Okay. So the next production of A that you will be trying is this one, AABA. S gives. So the next production you will trying small a, capital small a, small b, small a, and then this is A. So as you can see, this AA is matching and this B is matching. This A is not matching this B, right? So that's why this particular production is also failure. So now you got to know that this is also the failure, right? So see, you have tried this B, this was failure. You have again tried the next production of A, which was again failure. Now, since all of the production of A has been adjusted, so this A is a failure itself. So that is why you will say that since this A is a failure, let me just backtrack on S now. So now you will backtrack and you will try the different production of S, right? You will backtrack and then you will say, let me try. So this S is also the failure. See, let me just count the failures, right? The failure production. So this B was the failure first, and then this A was the failure because B was the failure, and there is only one B production. So since this is returning false, that's why A is also failure. So I tried the next production, right, of A. Now I'm saying that okay, A I have tried this. This is also the failure. So see, this B was failure. This A was again failure. Now this A is a failure. Because this A is a failure, that's why this S is also the failure, right? So that's why I'm just marking this whatever is the failure production. So basically the backtrack is defined like this. If a production is a failure, then we count it as a one backtrack. So here this A was the failure, that's why there is a one backtrack. I'm just making it a square making a square around it. And then this S is again a failure because one of the production of S, which was S gives capital A small a, this is again a failure. So that's why this is I'm marking it as a square bracket, right? Now let's just backtrack on this particular symbol now, which means that you have tried this. Now let me try the another production of S, which is capital C small e. Now as you know that this capital C will be giving you small a D, right? So this is matching, which is really great. Now capital D will be giving you B and then D. Okay, that's really great. So this D will return true. That's why this C will also return true. That's why this S will return true. And finally, this is success, right? Parsing successful. So how many backtrack you have here? How many backtrack you have here? You have one backtrack here, one backtrack here. Backtrack here means that how many productions got failed, right? This particular production got failed. 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 So there are 4 productions, or you can count with the square mark that there are four productions which got failed, right? So that's why the answer is 4. See, the answer is 4. Okay. So there's a failure here. Because of this failure, this B got failed, and A gives AB also returns false, right? This is also false. So this is fail, this is fail, this is fail, this is fail. So there are 4 fails, right? Okay. So there are 4 backtrack that you need to do. I hope you understood this particular question. This was the question number 6. Now let's just move to the next question, which is question number 7. So what they are saying, consider the grammar below. Will the recursive descent parser with the backtrack be able to solve the given string? This string? This is one of the very interesting question. They are asking whether the recursive descent parser with backtrack will even able to parse this string for this grammar. Let's just see. Okay, let's just see. So this is the very first kind of question where we are seeing this type of thing, right? So what we will do, as usual, we will start with the start symbol, which is E. Now, as you know that from this E, we will go to the very first production, which is T. So maybe due to the lack of space, I will start from here. Okay, E, that will go to T. Then it will say that let me now go to the very first production, which is int. Since int is not matching, that's why you will backtrack, right? Then you will try this int star T. So basically, you will backtrack here, and then you will be starting. You will be writing int star T, the next production. Again, this int is not matching this, so you will backtrack again. So anyway, this was also the common sense that this will backtrack, this will backtrack. So you could have directly written this, okay? With the little bit of practice, you will get to understand that you could have directly started with this. You could have directly written this state, okay? Because you know that anyway this will backtrack, and they are not asking the number of backtracks. They're asking whether it will like this particular parser will be able to parse this or not, right? Anyway, so let's just do step by step. This will backtrack, this will backtrack. So there's a failure here, there's a failure here, okay, now you got this. Now since this is matching, now you will proceed further, and then you will say that okay, this E will give you again T, right? T, and now this time this T gives int will be successful. Okay, let me write here. This T gives int will be successful. So just see here what is happening. This got matched, right? That's why I move further for this E. Then E gives T, T gives int. This also got matched. Since this has got matched, so that is why I will say this is returning true. Okay, this will return true. It means that it is success. See, for as per this T, there is no fault of this T. T is saying that I am successful. So it will return true. And now E will say, since T has returned true, that's why I will also return true. So this is success. Now it will just say that, okay, let me just match this with the remaining thing, which is plus, right? So these two has got matched. Now let me match this and plus. Now tell me, is this matching? Since it is not matching, so there is a failure. Now this is a fault of whom? There is a failure of whom? Is this T is a failure? This E is a failure? This E is a failure? This T is a failure? Who got failed? Tell me. See, this is not matching with this particular plus, right? So this is a part of this T. See, T will say, I will be successful only when this is matching, this E is a success, this is matching, right? Since one of them is not success, so that's why this T is a failure here. Okay. Interestingly, this E is not a failure. Okay, this E will say that the T is saying true, T is passing, so I will pass. I will not backtrack. There is no backtrack on E. There is a backtrack on T. So this will be E gives T. Now one of the production you have tried which was not successful. I mean, this was even the last production. So you will say that you have tried all the productions of the tree, right? All the production of the tree. So there's a failure. So you will say that this particular tree you have tried everything. Now you need to backtrack even at E, right? You need to backtrack even at E. So you need to basically say, let me backtrack at E, which means let me try the different production of E. So you will try E gives T plus E. T will try int. Obviously it will be failure. By the intuition you can say int start, these will failure. So the only thing that will get success is this, right? And then this is matching. So this E will go to T and T will go to int, which will again match, but this will fail, right? This will fail just like this. So this will fail with this plus. So which failure is this? The failure of whom? The failure of whom? Failure of again this T, right? So you will say that here also you have tried all the production of the T, because this is the last production. So you have tried all the production of the T. So this T got failed. It means what? It means that let me just backtrack at E. Now E also you have tried everything. So this E will say that, okay, I have tried everything. Now this production is not working. This production also not working, and earlier production was also not working. So E will also return false. So that is why this will, ultimately E will return false. That's why this will not get even parsed. Okay. So the parser will not recognize this. Parser will not recognize. Okay, let me just explain it once more. Probably you will understand, okay, a better way. See, this is int plus int, okay, in the bracket. Now let me draw the ideal, okay, the ideal tree that you're looking for. The ideal tree is you will start from E, then I think from this E to T, then this, okay, and then this E should be going to T plus E, right? So so basically from here this E should be going to T plus E, T plus E, then this T will give you int, this will give you T and then int, right? This is the ideal tree that you're looking for. But unfortunately, we are not getting this tree. Let's just see why we are not getting this tree. Okay. See, you will start from E. Using the recursive descent parser, basically we are not getting this tree, right? Then obviously from E to T, that's fine. Then obviously this will backtrack. So I'm not writing it even just to show you. So I'm not writing it, okay, because int will backtrack, int star will backtrack, because the first symbol is opening parenthesis. So I'm directly writing this, right? The last production you will try, and then this will not backtrack here. Till now I think things are fine. Now this is matching. That's really good. Now on this E, you will say that let me. So basically this is matching, right? Maybe I can just make a copy of this so that I can show you what is happening on the runtime, right? So this is matching. Now you're looking for int. So this E will again go to T. This T will again go to int. Great. This int and this is also matching. Now you're looking for plus. Okay. Now just see here, this will return success. That is why this E is a successful. Okay. E will also return success. And now this is not matching with the plus. Hence you will say that there's a backtrack at T. Okay. There's a backtrack at T. This is a mistake. There's a no backtrack at T. I mean, you should not backtrack at T. Basically, you should have been backtrack at E, right? See this E, if you could have tried the different production, which is let's suppose T plus E. Okay, instead of E gives T, if you try T plus E here, okay, see on this E itself, if you try, let's suppose on this E itself, you try T plus E or something, right? Then in that case, you could have gone to the success. But you are saying that you don't need to backtrack at E. Using the algorithm, what will you will say? You will say that okay, E is giving T is giving int. This is a success. So that is why E is calling just one thing, right? Which is T. So what will the code of E? E will be just saying that, okay, it is either E1 or E2. So E1 is basically true, right? E1 returns true. E1. So you will return if E1 is returning true, then you will return true, right? Something like this. So you will say that okay, if this is true, then I am true. Like, which means that it will say that okay, that this E will return true because this E1 is returning true. Now you will be forwarding this responsibility on T. You will say that it's a fault of T. Okay, that is where this parser is going wrong. So this parser is saying that you do not need to backtrack at this particular moment, which is E. You need to backtrack at T. Okay, you need to backtrack at T, which is wrong. So if you backtrack at T, you will be saying, okay, I have tried all the productions of this. Then you will be backtracking even at E. So you will say that T plus E, right? T plus E. Now because of that, you will say that okay, now again you need to restart, which means your input pointer will get restored. Okay, your input pointer will get restored to this int, right? And then you will say that okay, now this T will go to int, which will not match, and int star will also not match. So you will go something like this. This will match, and then this E to T and T to int, which will match. That's fine. But now this is a failure, right? Since this is a failure, so this T is a failure. So you will say that okay, for this E I have tried E gives T, I have tried E gives T plus E. Both of them are failure. So that's why this is a fail, which means the parser will not be able to recognize. You can even write a simple C code. Okay, if you want, write a simple C code, give this as an input. Okay, give this string as an input, and then let's just see that what you are getting, true or false. You can take it as a homework or take it as an exercise. If you want, you can write simple functions, right? 1, 2, 3, 4, 5, 5 functions you need to write. Just a main function, just call this. It's a very simple exercise, and then you can definitely check that this will not be able to parse the string, right? Okay. So that's how you can do this question. This is a very, very interesting question where the string is in the grammar, okay, or the language. The string is in the language, but still you are not able to parse. I mean, the recursive descent parser with backtrack is not able to parse, right? So a very good question, I will say. Okay, cool. So let's just move to the next question and let's just see if we are able to solve those questions. So let's just see this question. Consider the given grammar below. How many times we need to backtrack to parse the CAD? Okay. So this question is comparatively easy. They are just saying how many times we need to backtrack if we want to parse something like CAD on this particular grammar using the recursive descent parser. Okay. The string is CAD. So S will go to small c, capital A, small d. Then this C and this C is matching. So now this is A, B, right? This A is A matching. So this B and D is not matching. So whose fault? This is the fault of A. So you will backtrack at A, right? This is the fault of A. So you will try a different production of A, which means you will try this capital A gives small a now. So then C is matching, A is matching, right? And then this time D is also matching. So that's great. So this will turn true. So I think just one backtrack you need to do, right? So what is the answer? Answer is one backtrack only. Okay, so there is only one backtrack. Easy question, but you need to understand the parser to answer this completely, right? Now let's just see this question number 9. Consider the grammar given below. How many times we need to backtrack for this BCD? Okay, let's just see that for this small b, small c, small d, right? For this particular string, how many times we need to backtrack? Let's just see. Let me go to the next page. Let's just try answering this. So B, C, and D. Okay. Now let's just start with S. Now it will be B, A, B. This B and this B is matching. Now this A and this C is not matching. So you will backtrack, right? You will backtrack on this S because the production of S got failed. So you will backtrack on S. So small b, capital A. Now you will again say, okay, this B and this B is matching. Now this A will give you D. So this time this D is not matching. So you will backtrack on capital A, right? So you will backtrack on capital A, which means you will try the different production of capital A. This B and this C is matching, right? And then this capital A will go to D, I think. Then D and D is matching. So how many backtrack you are having here? Just two backtrack, right? This is a backtrack on S. This is a backtrack on capital A. Okay, and then 2 is the answer. So there is a backtrack, there is a backtrack. So answer is 2. Understood? Cool. Let's now see this question number 10. So what they are saying, consider the given grammar below. For which of the following input strings backtracking will be required? Okay, so these are the 4 options which are given to us, and now for which of them the backtracking will be required. So see, this grammar is given to us, right? So now let's just check, do we really need the backtracking for ACC to pass this ACC? Now see, by default the parser is recursive descent parser with backtracking, okay? Now don't worry about the parser. See, first you will go to capital A, capital B, small d. This capital A will go to small a, that's really good. This capital B will go to small a. So here you need the backtracking at least at this, right? At least at this B. And then later on you may need even at this S, which is fine, but at least one backtracking is needed here. Because this capital A is producing small a, which is fine, but this capital B is producing small a. So this B is a failure, right? This B is a failure. So that is why there is a backtracking here, right? So that's why you will say that this is answer. But since this is MSQ, there may be the multiple answers. Let's just see if you really need the backtracking for the CACD. So capital S will give you capital A, capital B, small d. This will give you small a, right? The very first production is small a. Now this is CACD. So this is not C. So that's why you may need the backtracking at A. I mean later on you will try this B also, and then you will say this A is a failure. So you will even say that, okay, let me try with this, right? Maybe you will be ultimately needing the backtracking at S, but that's fine. But at least one backtracking that you need, right? So that's why B is also true. So you also need the backtracking at this string also, right? Now what about this small c? Small c is, what about this option C? Option C is AAD. So this capital S is giving you capital A, capital B, small d. This will give you small a, which is matching. This B will give you small a at first, which is also matching, right? Which is also matching, and then small d. So there is no backtracking required for this small a, small d, right? So there is no backtracking required here at option C. What about the option D? Let's just check. So this is capital S, which will give you capital A, capital B, small d, right? And then this capital A will give you small a. This capital B will give you a small a first. So this is matching, but this is not matching. So you need to backtrack at C, and then you will say it is successful. So at least one backtracking again you need at this D also. So that's why A, B, D is the answer, right? So A, B, D are the answers. Okay, this was the MSQ question. Let's now see this question number 11. So what they are trying to say, they are saying that there are 2 rules are given in this grammar. Then they are saying how many calls to S parser needs to make in order to parse this. Okay, So by default, this is recursive descent parser with backtracking. Okay. So for all the questions, just assume the parser is same. Now let's just see that how many calls to the S we need. So see, there will be very first call to S that we need from the main function, right? So that is why you will say that, okay, the very first call to S, and then which will be ASB. And since this is matching, so that's why you will say now again, this is ASB. So I think till now three calls till now, then this is matching. Then this will again be going to ASB, but this will backtrack, right? This ASB will backtrack. So these are the 4 calls till now. So I'm just circling it. If this is a unique call, I'm circling it. So till now 4 calls that you have made, and now it will be the backtrack, right? Now it will the backtrack. So on this backtrack, you will see that what is happening. This is S, which is ASB. This is also S, which is ASB. Now this S was ASB, but it will backtrack, and now why it will backtrack? Because this A and this B is not matching. So now it will be BA, right? Now it will be BA. So this these are the 3 calls. Now this is not a new call, okay? There is no new call to S. This is just BA. So S has first tried ASB, and now we are saying that this ASB got failed. So that is why this S itself, see, there will be the S which will be trying ASB. So this is a call to S, right? This is a call to S, and now it will try BA. Now it is the next production that S is trying. So there is no new call. It is not a new S. It is just an old S which is trying the new production, which is BA. Okay, there is no call to S which is happening. Okay, there is a no new call. So only 4 calls has been there till now. So A was matching. This B is matching. This A is also matching, and then this B and this B is matching. So everything is matching. So only 4 calls, right? Not 5 calls or something. So 4 is the answer, right? 4 calls to S in order to parse this particular string. Easy, but very good question. I hope you understood. Okay. Now let's just move to the next question, which is saying that will this recursive descent parser with backtracking recognize the sentence ABC? So there they have given some grammar, and the parser is recursive descent parser only. Will it recognize this ABC? Let's just see. It is very, very interesting question. Let's just see, will it be able to recognize or not? See, this S will be giving you capital A, small c, right? And now this capital A will be giving you small a, because this is the very first thing that you need to do. And then what you will say, that this small a and this small a is matching. So now that's why just understand this carefully. That's why this capital A will say that it's a success. Why? Because if capital A is calling, see, capital A is calling this match A, this is A1 and this is A2, right? So it will say that, okay, if A1 is true, if this production is true, then it will say that, okay, this A1 is true. If A1 is returning true, then it will say return true, isn't it? So this capital A is returning true directly. So here you will not get a chance to try this AB, okay? You will not get a chance to try this AB. So that is why this capital A is returning true. So hence you will say that here you will say that this is true. Now you will try to match, this C with this B, okay? You will try to match this C with B. Since there is a fail, that's why you need to backtrack. But there was only one option for S, and you can't backtrack on S. So you will say that there is a fail. So this was true, and this is fail, right? I mean, this is not matching. So ultimately, this is basically false. So ultimately, it will be returning false. Okay. So that's why this parser will not be able to recognize this ABC on this grammar. Okay. Maybe I can just explain you once more, because this is really a good question, and this is a very first question of this type, right? So let's just see what is happening here. This S will be calling 2 things, right? I want to parse ABC. So S will be calling capital A, and then it will be calling 2 things, which is match C, right? First it will be calling capital A. That's how the algorithm will work. Now capital A will be calling match A. This is the first thing that it will be doing, right? Since this is true, this is matching, so this is true, that's why it will say that it is true. So this will return true, right? This will return true. So here it is returning true. And when can capital S return true? Whenever both of them are returning true. Now this match C, okay, match C will say that this is not matching, hence this will return false. Okay. Now basically this is returning false. It means that you need to backtrack on this, but there is no other option. So ultimately it is returning false only, right? Ultimately it is returning false. So that's why it won't be able to parse, because in the main function You are saying that let's just call S, let's just match dollar, and and if both of them true, if A and B, A and B, A and B, then you will say parsing successful. Okay, parsing success. Then you will say parsing success. But here this S is false. So that's why parsing is not successful. Okay, so that's how the algorithmic wise it will work. I hope you understood that how the algorithmic wise it will work. See what is happening. Let me again try to explain you. Here it's very interesting, right? Here this is not able to parse ABC. Very simple string, but it's not able to parse because this S is basically capital A small c, and then this capital A will say small a. Now, because this is success, right? This small a is matching here because this is success. That is why you are not backtracking on this a. Suppose by chance if you backtrack on this a and then you try a b, then it's great, right? Then it's matching. So this matching, but you do not get chance to backtrack on this a. That's the problem. Okay, so that is why it will return true, and then this will not match. Obviously, this will not match. So it is returning true. Okay, it is not matching with b. See, that's the thing that was happening earlier also. If you remember, maybe I can just tell you in one of the question that we did. Uh, yeah. So see, here also it was not able to parse this string. Why? Because see, this is our ideal tree. I mean, if this could have happened, then it would have able to parse, right? But the problem here is that this e, okay, if you remember, this e was returning true, and I was not backtracking on the C. If I could have backtracked on the C, then I could have tried this T plus E here. But here this E is returning true. And that is a problem actually. I mean, since this E is returning true, this returning true itself is a problem. Why? Because if it is returning true, then I'm not getting chance to try the other production, which is T plus E here, right? See, ideally after this I should have tried T plus E, but I'm not getting a chance to try T plus E because this is returning true. So hence there's a failure on this T. So I will be backtracking on this T. And since all the productions, okay, all the production, yeah. So I will backtrack on this T. T has this last production, which is in the parenthesis capital E. So all the production of tree has been tried. So I will be backtracking on this E, and all the productions of E also has been tried because this is the last production. That's why it will return false. So I'm not getting a chance to backtrack on the C. So that is a problem, right? So similarly, let me just go here. Similarly, like that's the same problem that we are facing here also, right? Let me go to that particular slide. See here, this is returning true, which is a problem. If see, what is the ideal tree? The ideal tree could have been look like this. See, this is the ideal tree. Ideal tree could have been capital S gives capital A, small c, capital A gives small b, and then this is small c, right? So this is the ideal tree. So which means if I could have backtracked on this capital A, that is good. But I'm not getting chance to backtrack on this capital A. Okay. So we are not getting chance to backtrack here. That is a problem. Okay. So for this particular question, what we are saying, so we will not be able to, will this parser be able to parse? Then what is the answer? The answer is no. Okay. No. This is the answer. Now let's see the next question here. So also you can see the answer here. So as you can see that they are saying that the non-terminal, see they are saying then the limited backtracking algorithm will not recognize the sentence ABC. The non-terminal as called at input position 1, which means initially it was called at this position, input position 1, will call at input position 1, will call A at the input position 1, right? Now you will call, I mean S is calling, S got called and S will call A. Using the first alternate, which means the first alternate is this one. Using the first alternates, A reports the success and moves to the input pointer to the position 2. Okay, so A reports the success and then it says that okay, it is a success. So it is a success, and now the input pointer is here. Okay, so you have called this, and then this C does not match with this B. Okay, that's the problem. This C does not match with this B. Interesting, right? Now let's just see this question here. Here what I did, instead of writing a, okay, instead of writing a b, I'm writing capital small ab and then a. So basically the difference between this question and this particular question is only that, so earlier, this is the earlier grammar, the question is as it is same, the only difference in the order of the production. Okay, so this is earlier, this is earlier, and now we have this. Let's just see that now are we able to parse. So what do you think? See, this capital S will go to capital A small c, and then this capital A will say that, okay, let me go to AB, right? Let me go to AB. Since this A is matching with this A, this B is matching, and this C is matching, so it is able to parse. So now the answer is yes. Now the answer is yes. Okay, just because we are altering, okay, we are changing the order of production, the grammar that is, the language it is recognized is basically changing, right? Hope you understood. Now let's just see this question. What they are saying, will the recursive descent parser, again, will it be able to parse this string? This is also very interesting question. Let's just see if you can solve this. Okay, let's try it out. So capital E will give capital T plus and capital E first, right? Now this capital T will give you, okay, will give you this, which is actually will backtrack anyway. So let me not write it because this is not matching with this. So it will backtrack. So let me write the next thing directly. Okay, it will be like this. Now this is success, right? Because this is matching. See, this is matching this end. So this is success. Because this is success, it will say that I am successful. Okay. Now it will match this plus with this star. Tell me, is this matching? Since it is not matching, so that's why it will backtrack. Okay. This is success here. But this plus and star are not matching, so that's why it will backtrack. On which terminal? So like which terminal got failed? This T, this E, this E, which one? This E, right? This E, because one of them has got failed. So now it will try the next thing, which is just T. And then T will try, anyway, like it will try this, but it is not successful. So it will try int, right? I mean, there will be backtrack on this, but that's fine. It will try int. Now this int is again successful, right? So it will say that, okay, again success, I'm successful. Now this E will return. See, interestingly, this E will return true, which means this E will also say that I am also successful. What is the reason? The reason is that, okay, let me tell you the reason why this E will also say that I am also successful. See, this E has called this T, right? E has called this T. If T is success, then E is success. So this is just like the second production, right? So it will say I'm successful. It will say I'm successful, which means it will return true. But does this mean that the parsing is successful? No, right? See, the input was int star int, right? This is the input. Okay, let me write it here. So this is the input. Now what you will do? You say that, okay, this int and this int is matching. So now the remaining input is this. Obviously it is ending with some special symbol. Let's suppose $. Now in the main function, just look at the main function. What does the main function has? In the main function, you will say that, okay, you will call this E. Let's suppose this is E, and there is a B, which is match $, right? Match $. And then you will say if A and B is success, then parsing success. Tell me what will happen. See, this particular, this is success. This particular A will return true, right? This is true. I agree with you, which means this is returning true. But is the next symbol $? Is the next symbol $? Since the next symbol is not $, which is star, that's why it will say fail. So this string will also not be recognized by this particular, I'm using this grammar by the recursive descent parser. So what is the answer? The answer is no. Okay. This is the answer. Let me just explain you once more. Okay. So what is happening here? That you wanted to parse int star int. Okay. You wanted to parse int star int. Now this E will try. See, ideally E should go to T, right? E should go to T, and then this T should go to, I think, int star int and so on, right? But the problem here is that I mean E should go to T, that's fine. I mean till this point we will be having, and this T should go to finally, I mean this is the ideal tree. Let me write the ideal tree. See, you don't need to write the ideal tree in the exam. I'm just telling you what is the ideal tree. This is the ideal tree, right? But the problem with us is that we are able to get this, but the moment we try this T, this int is successful. So we are not backtracking on this T. We are backtracking directly on E. Okay, I mean we don't need to backtrack because this was successful. So let me tell you again what is happening. This E, right? This E will be trying T plus E first, but ultimately, as you know, that this T will be trying int, and then this plus is not success. So that's why it will backtrack, right? It has to backtrack to T. Okay. Now this T will be trying anyway. This was failure. Now it will try int. Now since it is trying int, that is why it is success. It is also success, but ultimately it is a failure. Okay. At the end, it will be the failure because it is not the next symbol is not the dollar. Okay. I hope you understood. Maybe you will get to understand more with the examples. So if I just ask you, let's suppose in this particular question, if I just ask you that, can you give me a string which is not parsed? Here, I think if you give me, let's suppose int plus int, will it be able to parse int plus int? No, because E gives T and then T gives int. It is success, right? It is success. So it will say it is success, but ultimately it's not dollar. So int plus int itself won't be able to parse, won't get parsed using this recursive descent parser on this grammar, right? Okay, hope you understood. Cool. Now let's see more examples, and then you will get to understand more about this particular parser. This is just a algorithmic parser which behaves just in very simple algorithm. Okay, once you understand the algorithm, you will get to understand this parser. Now let's see this particular question which I have taken from Berkeley University. So what they are saying, that first, unlike the production that we studied in the recursive descent parser, is sensitive to the order of the productions. That is, recursive descent parser may behave differently, okay, when the production is rewritten from this to this, right? Okay, so what is the question? To see the order of production matters, consider the following grammar G. Note E is the only non-terminal in this grammar. Also, ID E denotes the array elements. Anyway, like let's not worry about it. So what they're saying, give one sequence of tokens that belongs to this language, okay, language of this grammar, but it's not recognized by the parser. Can you give me one string which is generated by the grammar, or maybe which is in the language of this grammar, but not recognized by the parser? Can you give me one string? The answer could be ID, right? This is why, because for this string it will go to ID, okay, and then this will say, okay, this is success. E will say I am successful, but ultimately this is not the dollar, right? So you can say recursive descent parser, recursive descent. By the way, what does this descent mean? Descent means top down. I mean, you are going down. Okay, that's what descent means. That's why we call it descent, not the ascent, right? Recursive descent parser will, with backtrack, right? With backtrack will not be able to parse this. Right? Easy, right? Very good question, but you need to understand. I mean, this will be easy question if you understand the recursive descent parser really well. Okay. Now let's see this question. What they are saying? They are saying that in this particular, note that there is no left recursion and all. Now they are saying how many calls to f is needed if the input is 3. Let's just see how many calls to f. Again, this question is from the Berkeley University. So how many calls to f is needed? Let's just see. So this E will be calling T plus E. See, the input is 3, right? 3 means int. Okay, 3 means int. Now this T will be calling f into E, and then this f will be calling int. So there is one call here. Okay, I'm just making a circle here. There's a one call here we need to do for f. So this is the first production, and T is having the first production, which is f into E. This is success. Now this is the failure. Okay, so this is a failure. So the failure of whom? Failure of F, or failure of E, or failure of T, failure of whom? See, this is a failure because this is not the dollar, right? So failure of T. So since this got failed, okay, since this got failed, so you need to backtrack, which means you will try a different production of this T. So you will try a different production of this T. So F into E you have tried. Now you will try F divide E. So again, this will be int. Okay, this will be a new call. But this will be a new call. But again, this is not the dollar. So that's why this will get failed. So again, you need to backtrack, right? And then you will be trying this particular production, which is E gives T plus E. And then the last production is F, which is int. Okay. Now again, this is success. Again, this is success. And this is a new call. So I'm making a circle here. So this is success. This T is successful finally, right? At least T is successful. Now, because this plus is not the dollar, so whose fault it is? This is the fault of whom? Can you tell me? Okay. So see, this is not this is not the dollar. So that is why this is the fault of this capital E, right? You will try the different production now, which is capital T minus capital E. So see, there are three now. Now you will try capital T minus capital E, right? The different production. Now again, because of this, there will be three more, right? There will be three more, and ultimately you will say that okay, this minus is not the dollar. So this will again be failed, right? This capital E again be failed. So there's a three more. Okay, I'm not writing those, but there are three more calls to F. Three more calls to F, right? And then you will say that okay, here this is minus, which is not dollar. So you will backtrack on this E, which is T, right? The last is T. Now again, because of this T, there are three more calls, right? I mean, this T will first try this, then this, then this, and finally this will be successful. So three more calls you can say, okay? So three more here. Calls to F, and then it will be successful. So once it is successful, it will say, okay, this will be successful. Now you will be having basically something like this, right? You will be having, let me also write it, something like this. So you will say that it will be E, T, and F int. Okay, this is not a new call. I mean, I have already counted it. Okay, don't count it. So you will be having, it will be success, success, success. So finally it will be successful. So how many? Three here. And then whenever you are trying this particular production, then again this three, then again this three. So total 9 calls. Okay, total 9 calls to F. Okay, good question. So what is the answer? Answer is 9 calls. Now let's see a new question. So this question and the previous question is almost same, but it might be little more lengthy. Okay, so they are asking for this 3 into 3 string. Just solve this question and comment out your answer. Whatever answer you are just getting, just comment out. Okay, comment out your answer for this particular question. This question might be little lengthier than the earlier question, but just try this question so that you get more comfortable for this particular parser. Okay, remember this question might be lengthy also. Okay, but comment out your answer. I don't have the answer with me, but you can comment it out, right? Okay, just definitely try this out and just comment out your answers. Now let's see this question, which is a MSQ question. What they are saying? Consider the grammar given below. Which of the following string can be generated or can be recognized by the recursive descent parser with backtrack? So with this grammar, and the parser is recursive descent parser. Okay, so can it recognize recursive descent parser? Can it recognize this particular string? Let's just see. Obviously this how it can recognize, because this is not even in the language, but still let's just see. This is AA. This A is matching with this A, and then this A is not matching with the dollar, right? Ending with the some special symbol, whatever you want to say, hash, dollar, star, whatever, right? But it's not matching, so it will obviously not recognize. So this will not recognize. What about this A? So this A is matching, A is matching, this A is matching, A is matching, yes. And then this is ending with dollar. So anyway, the final dollar will get matched, right? So this is getting matched. What about this 4 times A? This A is matching. Interestingly, this is also matching. So these two A's are matching. Now, interestingly, it will say true. Okay, it will say true. It will say true. Since it is saying true, that is why ultimately it is not the dollar, right? Ultimately it will match with the dollar. It is not the dollar. So that's why it will say that, okay, you need to, basically the parsing will be failed. I mean, you cannot parse this particular string. Although this string is in the language, right? This string is in the language, still it is not able to parse. So no. What about triple A's? So this A, again, these two A will get matched and it will say true. But still again, ultimately this A is not dollar, and also this is not in the language, so it will not anyway get parsed. But still, like according to algorithm I'm running, so this A will get matched, it will return true, but then this is not the dollar, so it will also not get parsed. So the only string actually it can parse is A. There is no other string from this language, right? So whatever you write, either you write 4 times A, you write 6 times A, because these are even numbers of A's, right? It won't be able to parse any other string. So B is the answer here. And you can say this parser can parse only A. Okay. Now, let's just see a next question which I have taken from Ullman. Now, in this question, this small a I have written, or maybe the book has written later on. Okay. So you might be knowing about Ullman. He is a Turing Award winner. He has written multiple books. Okay. And on DBMS also he has written books, on compiler design also, I think on TOC also. So he has written multiple books. He's a Turing Award winner. Okay. So let's just see what they are saying. They are saying the grammar S gives A as A. Now, or small a generates all even length strings of A. We can devise a recursive descent parser with backtrack for this grammar. If we choose to expand by the production A first, if we are doing this first, then we shall only recognize A. That was the question number. The previous question, right? So if we are doing this first, then we shall only recognize A. Okay. Okay, that's what we have seen. Thus, any reasonable recursive descent parser will first try this. Now, what they are saying, that show that recursive descent parser recognize input A, 2 age, 4 age, and this is 8 age, okay, 8 age, but not 6 age. So they are saying that you have capital S gives A, capital S A. This can recognize A. This can recognize 4 times A. This can not recognize 6 times A, but it can again recognize 8 times A. Okay, that's what we need to show. That is the question that they're asking. Okay, so let's just try with the input one. Input one means a small a. Okay, so let's just try with this first input, which is small a. Will it be parsing this small a? Let's just check. Input one, which is small a. Will it be parsing this small a? See, this S will be going small a, capital S, small a. Now blindly you can write like this. See, these two A's are there, so that's why it will expand till this point at least. First it will expand till this point. Later on it can may backtrack and these things may happen, right? Because these two A's should match, right? So now this capital S will again go to small s, small a, capital S, small a, and whatever you try, actually it is not a dollar, right? It is ending with a dollar. Whatever you try, it is not a dollar. So you will say this S is a failure, right? Now you will try a different production on this S. ASA was there. Now the difference production is A. Okay, A. Now you will again say that this. So maybe I can just copy, right? See. You will again say that this S was the failure. Now you will try A. Now you will again say that this S is again a failure because you have tried both the productions, which is ASA, and now you have tried A, which is also the failure because this is not the dollar. So that's why this is also the failure. So you will again backtrack and then this time you will try A, and then this will be successful, right? So yeah, there will be multiple backtracks, but ultimately it will be recognized as A. So A, success, right? Now let's just see 4 times A. Will it be able to recognize this 4 times A or not? Let's just see this quickly. Okay. So A was success. Now let's just see 4 times A. Okay. For now, let's just suppose that it is 3 times A. Can you tell me what is the very first thing this parser will do? It will immediately expand till this point, right? See, this is 3 times A. So it will immediately expand till this till this 3H, because it will be matching, and then it will be immediately expanding till this 3H, right? If it is 4 times A, actually it will immediately expand till this point, and later on it may be backtrack, but that's fine. Okay, first it will expand till this point, right? Okay, now let's just check what is happening. So they are saying it is 4 times A. So see, this is matching. Now this S will, whatever you try, actually it is not a dollar, so this S will be failure, right? So that is why you will say this S is a failure. So you will not be, basically it will get failed at this S. So you will not be using this particular production, right? I mean ASA. So that's why you will be using the next production, which is, what is the next production? A. So on this S, let me just tell you what will happen. So basically on this S, you will be using the next production, which is A. Now what is happening here? This S was the failure, right? Let me just mark it with the different color. Okay. Now you are using A. Now these are the 4 A's which are matching, but this A is not the dollar. So this S is actually completely failure, right? Complete failure. So that's why you will say that, okay, this S you have tried as ASA. Now you will be trying which one? You will be trying A. So what will happen now? Let me just tell you that now you will be trying A on this S, right? So on this S, which is the third S from this top, on this S you will be trying A. Okay. Now here what will happen? You will say that see, now this is okay, this is okay, this is okay, this is also okay, but this A is not matching, right? This A is not matching dollar, because my input is A dollar. Okay, this is my input. Now tell me, interestingly, if this is matching, this is matching, this is matching, this is also matching. If this is not matching with the dollar, then it is a fault of whom? Is this S got failed? This has got failed, or this has got failed? Let's just suppose, let me just name it S1, S2, S3. Can you tell me which S is a failure here? S1, S2 or S3? S2, right? Because something from S2 got failed. So you will not backtrack here at S3 or something. I mean, we have already done it. But anyway, this S2 is failed, right? So this S2 is failed. So that's why instead of, so this was ASA. So instead of ASA, you will be trying A. And then this time you will say, okay, everyone is success. So finally it is success. So it seems like that 4 times A is also successful. Now let's just try input 3. Which is 6 times A, okay, which is 6 times A. So input 3, which was A dollar, right? See, what is the ideal tree here? Let me just write ideal tree. Just, I mean, you don't need to write it, but just for the sake of explanation or just for the sake of understanding that what is happening, we are just writing, okay? Basically, you will say that, okay, this should be the ideal tree, right? This should be the 1, 2, 3, 4, 5, 6. Okay, this should be the ideal tree. But it seems that the question is saying the parser will not be able to generate this ideal tree. Let's just see if that is true. See, this capital S will first go to this, and since it is 6 times A, that as you know that it will be basically generating 6 A's, right? 6 A's first. 6 A's. So basically it will be a long tree. I think I have already the diagram, so I can just copy paste the diagram. So that is the 6 A's. Yeah. So there is some diagram which I have taken. So let me just copy paste this diagram directly. Okay. So this is the very first thing that parser will do. Now you will say that, okay, all of this is matching. These are the 6 A's. So whatever you do at this S is a definitely failure. So you will be backtracking, right? So you will backtrack on this S. This S is completely failure. So you will say, now ASA you have tried. Now let me try A. So basically you will say that let me now try, we have tried ASA, let me try A. Is this fine to everyone? Tell me. See what is happening. This will generate, this is the very first step. And now this S is a complete failure. Now you are trying the next step, which is A. On this S you are trying A. Okay. Now see, these are the 6 A's. So this A is not the dollar. So that's why this S, you have tried ASA, you have tried A. So both are the failure. So what is the next thing? What is the next thing? You will try on this S, you will say that, okay, ASA you have tried. Now on this S, so maybe I can just copy this. Okay, so on this S, you will say that, okay, ASA you have tried. Now you will be trying AA only. Okay, let me try A. Now these are the 5 A's and this is 6 1. So this is not the dollar. So that's why there is a fail. Now this is a failure of whom? Let's suppose this is 1, 2, 3, 4, 5. This is a failure of whom? S5, S3, S4, S2, S1. Which one got failed? Basically S4 got failed, right? Because S4 is generating A, and then this A is not the dollar. So S4 will get backtrack here, interestingly. Okay, so which means this is the failure, right? So because this is a failure, so which means you have tried ASA, now you will be trying AA. Okay, on this S4 you will be trying AA now. So let me just remove this. Let me try AA now. Okay, so which means this was the failure. You have tried ASA, now let me try A. Okay, now if you try A, let me know which one is the failure now. Which one is the failure? See, now you will say that this is A 4 times A 5 6. Now this is the failure, right? I mean, this is not the dollar. Okay, so see, this is not the dollar. Since this is a failure, so you will say that on this S, interestingly, on this S you will be trying the next production, right? Which is ASA. Now you will try on this S, you will try A. So here let me just tell you, the next thing that will happen to you is something like this. See, this S was the failure, right? So that's why on this S you are directly trying A, and because of that the whole thing is basically getting mashed up. See, now if you try A, then what will happen? Then you will say that, see here, it will match, and then ultimately it is basically, it will return true, but this is not the dollar, so it will false. See, this is ideal tree, right? Which I have written here, which is S1, S2, S3. On S3, if I could have tried A, then I think I could have saved my thing. So 1, 2, 3. So on S3, actually, we are not even getting a chance to roll back. S3 was saying I am success. And S2, at S2, we are getting the chance to roll back. That is the problem, right? See, in all of the example, why it is not able to parse? Maybe because that wherever I needed to actually backtrack. See, on S3, I should have tried A, right? I should have tried it and then I should have saved it. But on S3, it is success. And S2, on S2, I'm backtracking. That is why ultimately it is a failure. Okay. See, in whatever cases we have seen, let me just remind you. Yeah, see here that what is the problem here? See, we are saying that this E will try this capital T, then it was trying capital T plus E, and then this E was successful. Because this E was successful, I'm not able to roll back on this E gives T, and then that is why this is a problem, right? I mean, this E is successful, I'm not getting a chance to roll back on this E. So that's why that was the problem here. Similarly, here also, I'm not getting a chance to roll back, right? I'm not getting a chance to roll back out on S3. So we are not getting chance to roll back on S3, right? So the answer is no. Okay. Very good question. Actually, this is quite a difficult question. So if you want, you can take it as an optional question, because this is this is one of the very difficult question, and the purpose of this question is just to make sure that you understand this parser really very well. Okay, this question has been taken from Ulman, and it is really a very difficult question. Even on Stack Overflow, there are multiple people which are asking about this question, and this diagram which I have taken. Okay, in this diagram, these things are from Stack Overflow only. On Stack Overflow, like multiple people were asking about this explanation of this particular question, because this is really a good question. So if you are not able to solve it, it is completely fine. Okay. Now let's just move to the next question. So what they are saying, which of the following is or are true? A recursive descent parser is a sensitive to order of production. What do you think? Is it sensitive to order of productions? Answer is yes, right? Answer is yes. It is true. A recursive descent parser with backtrack is a top-down parser. Yes, it is a top-down parser. Is this a predictive parser? No. Okay, no. What is a predictive parser? We need to understand, we need to see the predictive parser in the future lectures, but the predictive parser actually make a call based on the next input symbol, which means, see here what we are doing, let's suppose a gives something, right? Something like this. Then here what we are saying, we are directly going to this, and then we are seeing that, okay, is this matching? First we are calling, and then we are saying, is this matching to the, let's suppose my input is just B. Is this matching B? No. Then we will backtrack, and then we will say that, okay, now things are fine. But predictive parser will not first call. It will call based on the next input symbol. Okay, it will predict that which one to use. Any human being can tell very intuitively that, okay, it is starting with A, it is starting with B. You need to start with B. So that's why it is a common sense to directly go for this. Right? That's what the predictive parser does. It basically directly goes for this. We will see this later on, but yeah, this recursive descent parser is not a predictive parser for sure. Okay, it is blindly calling. So that's why it is no. Recursive descent with backtrack do not work with the left recursive grammar. As you know, it will go to the infinite loop. So that's why this is also true. Right? This is also true. So what are the answers? Answer is A, B, and D. Okay, these are the answers. Understood? Really a very good question. And we have solved all of the questions very nicely. And I hope that you understood this recursive descent parser now completely. If you have completely understood this, then please comment that you have understood. If you have loved this session, then just comment that loved it completely. You have understood, then just let us know what is the feedback, okay? Because it really motivates us. So just let us know your feedback if you have understood this particular parser completely. So these are the 20 questions which I have taken from different sources. Okay. So thank you for watching. Just let us know in the comments that if you have understood everything. Thanks.